Hello everybody. In this video we're going to continue our discussion about what science is, but we're actually going to take a look at the scientific method by pitting two historical figures against one another. We're going to take Galileo and his ideas of how things fall versus Aristotle and how he thought things fall. And we're going to go ahead and run through an experiment, look at some of the numbers, bring in these ideas of uncertainty to figure out if we can actually do an experiment to see how nature is behaving. I'm pretty happy with the slides I put together here. I hope we're gonna have a little bit of fun. So let's go ahead and dive right in, what I'm calling Galileo versus Aristotle. So here we have Aristotle, and Aristotle adhered to what became known as Aristotelian thought. This is all going back to Plato and things like that, but the idea of one of the foundational ideas of Aristotelian thoughts is that there is a perfection that must be upheld. That's what logic tells us, that the heavens must be perfect, and anything that's changing is clearly not perfect. So when you drop something, so if I'm going to sit here and drop something, whenever it falls at a constant rate. So here we have Aristotle, and he's thinking that if I drop this ball, it's going to fall at a constant rate. Galileo, however, is sometimes referred to as the father of modern science, the father of experimental science, because he was one of the first people to really start doing experimental empirical science. A radical idea of why don't we observe nature, listen to what nature is telling us by documenting what's going on, our observations and measurements, and allow nature itself to give us information about how nature operates, which is really what we're doing in science. So Galileo is thinking, I don't know if you're exactly right, Aristotle. What if it's different? What if things change their speed as they fall, so-called accelerate? So I don't know if you're right, but we can do an experiment to see if that's right. And that's really what we're trying to do here, is we're trying to go through the scientific method, which is what Galileo is proposing. So perhaps whenever you drop things, they accelerate as they fall, they speed up. All right, so let's look at the two different ideas. Let's come up with some hypotheses, put an experiment together, and be able to test the prediction that our hypothesis gives us, our idea of how nature operates. Let's start with Aristotle, since it's the older and perhaps the simpler of the two ideas. Aristotelian thought, logic your way to every phenomenon in the universe, so you only need logic. Forget observing nature, logic will get me there. And logic told him that nature has a perfection to it, and therefore things must fall at a constant rate. Hypothesis is pretty direct from right there. Objects fall at a constant speed. They do not speed up or slow down. So how could we test this? All right, let's go drop some things and see how they fall. We will drop objects from a series of different heights and time how long it takes for them to hit the ground. And then we'll look at that time data. So if objects fall at a constant speed, what does that predict? Well, if I drop something from 10 meters, and then I drop something from 20 meters, it should take twice as long to hit the ground. If it falls at a constant speed, if it takes double the distance, it should take double the time for it to hit the ground. All right, so now we have the Aristotle hypothesis. Let's go with the Galileo hypothesis. I don't know if things fall at a constant or accelerating rate. That's the idea he's trying to test. Notice it's not really making a whole lot of assumptions here either. Hypothesis, well, let's choose the opposite one. If they're not falling at a constant speed, they must be falling with acceleration, meaning that they're speeding up as they fall down. So the experiment, again, same experiment. Drop objects from a series of different heights and time how long it takes for them to hit the ground, and that timing data should tell us if things are falling at a constant rate or an accelerating rate. The prediction, if they're falling and falling faster, if they're accelerating, speeding up as they fall, if I double the height, it should take less than double the time, because it's moving faster so it can traverse that distance quicker. All right, have our Galileo hypothesis and our Aristotle hypothesis. The experiment is the same. Let's conduct it. Here we are. Let's go drop some things off of a cliff. And this is trial number one. Let's drop objects off a 10-meter high cliff. We're not just going to drop one object and take the time, because as we saw, you want to do repeated measurements. And then that way you can get an idea of what the average measurement is. And you can actually get a little idea of what the uncertainty in your measurement would be, because there's no such thing as a perfect measurement. You can't time these things exactly the same every time. There's no such thing as a perfect measurement. So we're going to drop things 10 times. If you're really doing this, you'd want to increase the number. 10 is probably not sufficient, but this is just an example. So drop something from 10 meters. It takes 1.38 seconds. Do it again, timed 1.39 seconds, then 1.35 seconds, then 1.16 seconds. That's a little bit different. There's some variance between these different measurements, talking about the precision and some of the error that's entering things. So I drop this 10 times. I'm going to average all these numbers together. So I get an average, a mean of 1.45 seconds for something to fall 10 meters. And by looking at how much each one of these data points differs from every other data point, I can see the uncertainty in those measurements because they are different, and I can quantify that. The way that we do this for the people that really like statistics is we use the standard deviation. And in that case, the standard deviation, our uncertainty, gives us a plus or minus 0.2 seconds. Okay, there's our first height. Now, let's drop it from twice the height. So we're having a little bit more fun, and we're going to do the same experiment, 10 drops from a height of 20 meters, and time how long it falls. Trial 1, 1.86 seconds. Trial 2, 2.05 seconds, so on and so forth. Average those 10 together. You had an average fall time of 1.98 seconds, and this time the uncertainty came out to be plus or minus 0.013 seconds, a little bit less. Maybe because the times were a little bit longer, it was a little bit easier to use the stopwatch that neither of them had to actually get better data. So a little bit lower uncertainty. Okay, we ran our experiment. Let's analyze our results. Let's evaluate the hypotheses. So remember, our idea that Galileo has is, I don't know if things fall at a constant rate. And we did the experiment, and we're testing the predictions that if things fall at an accelerating rate, they gain speed as they fall, then doubling the drop height should result in a fall time that is less than twice as long as the original drop height. So let's look at our results. Here was our 10-meter drop. The time for the fall 10 meters, 1.45 plus or minus 0.2 seconds. And you could go ahead and put that into the range. So 1.25 to 1.65 seconds. For the 20-meter drop, 1.98 plus or minus 0.013 seconds. Turn that into its range, 1.85 to 2.11 seconds. Now let's test the hypothesis. Let's double the 10-meter drop time and compare that to our 20-meter drop time. So let's double these values right here. So we have a range of 2.25 to 3.3 seconds. And we want to ask ourselves, is that more than the 20-meter drop? So is the 20-meter drop, is that going to be a shorter amount of time than double the 10-meter drop? So let's take a look, 1.85 to 2.11. Oh, that's certainly less. It looks like things were accelerating whenever they fell. Yes, let's accept Galileo's hypothesis that objects accelerate while they fall. However, if we double that uncertainty, these plus or minuses, and then compare the two results, and what we're really doing here, and I know I'm playing a little bit fast and loose and I'm not doing the full statistical testing, but I'm trying to demonstrate the concept here. So if I double the uncertainty, aiming for that, I want to be 95.5% confident that I can test that Galileo was right and that things accelerate as they fall. And I want to be able to have confidence in rejecting Aristotle's hypothesis. So if I were to double these uncertainties, then I'll leave it. If you really want to check it, you can double the uncertainties and then compare the two times. You can go through this again, and you're going to notice that the ranges overlap, which means that I would have to reject Galileo's hypothesis that things fall at an accelerating rate. And with the data that we have, the experiment that I have conducted, I'd be forced to accept Aristotle's hypothesis. Even though I know that that is not the correct one because we're here in the future. But what we need is more data. We need, or better data. We could do more precise data, beat down those errors, those uncertainties we have in our times, or we could continue the experiment and collect more data. We redesign our experiment, we go back at it. So let's repeat the experiment. This time, however, I'm going to do an additional 10 drops from a height of 40 meters. That's getting pretty high up there. So here we go. Drop something from 40 meters and time how long it takes. You have 3 seconds, 2.62 seconds, 2.96 seconds, so on and so forth. Come up with your average, the mean of 2.85 seconds. Has an uncertainty of plus or minus 0.21 seconds. All right, have some more data. Let's go back to our hypotheses. Let's reevaluate them. And let's see what we have. Now let's compare the 20-meter drop to the 40-meter drop. Larger distances, if things are accelerating, that bigger difference in the heights should really become more apparent. That's why I'm doing the 20 to the 40. So our 20-meter drop, here are the numbers, but I really want to hit that 95.5% confidence level. I want to be sure that Galileo is right and I can reject Aristotle's things fall at constant speed. So I'm going to double my error bars, my uncertainties. That gives me, for the 20-meter drop, a 1.72 to 2.44 second range. And for my 40-meter drop, it gives me a 2.43 to 3.27. And now I'm going to compare, double the 20-meter drop, and I'm going to get this range, 3.44 to 4.48 seconds. Is that more than the 40-meter drop? Well, that range is 2.43 to 3.27. This is smaller without any overlap. Whew, I feel more comfortable now accepting Galileo's hypothesis. Objects accelerate as they fall, and this time I can say that with more scientific confidence. I could push it even further with more careful measurement, more experiments. But I hope this was an instructive video for you to actually see and understand how we go about doing some hypothesis testing. It's one of those critical parts of science. So I wanted to give you a concrete example. Thanks for tuning in, and I hope that you enjoyed the video.